This lesson is to solve problems involving exponential growth occurs when a quantity increases by the same rate, r, in each period t. When this happens, the value of the quantity at any given time can be calculated as a function of the rate and the original amount. An exponential growth function has the form y equals a times in parentheses 1 plus r, close parentheses, raised to the power of t, where a is greater than 0, or a positive number. Y represents the final amount, a represents the original amount, r represents the rate of growth expressed as a decimal, so you change the percent to a decimal, moving it over 2 places to the left, and t represents time. The original value of a painting is $9,000, and the value increases by 7% each year. Write an exponential growth function to model this situation, then find the painting's value in 15 years. Step 1, you're going to write the exponential growth function for the situation. The formula is y equals a times in parentheses 1 plus r, close parentheses, raised to the power of t. We're going to substitute 9,000 for a, which is the original value, and 0.07 for r, the rate. Remember, that's the percent converted into a decimal, so we move the decimal value over 2 places to the left. So we get 9,000 times in parentheses 1 plus 0.07 raised to the power of t. Simplify and add 1 plus 0.07, and we get 9,000 times in parentheses 1.07 raised to the power of t. Step 2 is to find the value in 15 years. That's t for time. So we're going to plug in 15 for t. We get 1.07 raised to the power of 15 times 1,000. We're going to use a calculator, 1.07 raised to the power of 15, and then we times it to the 9,000, and we get 24,831.28. So the value of the painting in 15 years is $24,831.28. A sculpture is increasing in value at a rate of 8% per year, and its value in 2000 was $1,200. Write an exponential growth function to model this situation, then find the sculpture's value in 2006, which would be 6 years later. So step 1, we're going to write the exponential growth function for the situation. The formula is y equals a times in parentheses 1 plus r, close parentheses, raised to the power of t. So we're going to substitute 1,200 for a, which would be the original value, and then 0.08 for r. Remember, it's the percent changed to a decimal, so we move it over 2 places to the left, the decimal point 2 places to the left. So we get 1,200 times in parentheses 1 plus 0.08, close parentheses, raised to the power of 6. Remember, they want you to find it for the 6th year, so that'd be 6 years later, and that would be what we put in for t time. So we simplify inside the parentheses, and we get 1.08. That's 1 plus 0. And we use a calculator, rounding to the nearest hundredth, and we would get 1.08 raised to the power of 6, and then we would multiply that by the 1,200, and we get 1,904.25. So the value of the painting in 6 years is $1,904.25. A common application of exponential growth is compound interest. Recall that a simple interest is earned or paid only on the principal. Compound interest is interest earned or paid on both the principal and previously earned interest. Compound interest would be a equals p times in parentheses 1 plus r divided by n, close parentheses, raised to the power of n times t. A represents the balance after t years. P represents the principal or original amount. R represents the annual interest rate expressed as a decimal, so we change it to a decimal, moving 2 places to the left. N represents the number of times interest is compounded per year, and T represents the time in years. For compound interest, annual means once per year, so N would equal 1. Quarterly means 4 times per year, so N would equal 4. Monthly means 12 times per year, so N would equal 12. Write a compound interest function to model the situation given. Then find the balance after the given number of years. $1,200 invested at a rate of 2% compounded quarterly. Find 3 years later how much it would be worth. So step 1, you're going to write the compound interest function for the situation. The formula is A equals P times in parentheses 1 plus R divided by N, close parentheses, raised to the power of N times T. We're going to substitute 1,200 for P. That's the principal. That's the money we invested originally. 0.02 for R. That's the rate as a decimal. We moved it over 2 places to the left. 4 for N, because it's quarterly. It's compounded quarterly, which means 4 times a year. So we get 1,200 times in parentheses 1 plus 0.02 divided by 4, close parentheses, raise the value of 4 times t. Remember, we have to put n in the power as well as in the denominator. When we simplify 1 plus 0.02 divided by 4, you divide 0.02 by 4, and then you add 1 to it, and you get 1.005, and then in close parentheses is raised to the power of 4 times t. And they want you to find the balance after 3 years, so we're going to plug in 3 for t. So we have 1,200 times 1.005 in parentheses raised to the power of 4 times 3. 4 times 3 is 12, so it'd be raised to the power of 12. We're going to use a calculator, rounding to the nearest hundredth. We're dealing with money. So we get 1,200 times, and then we would do 1.005 times itself 12 times, and then we would times that by 1,200. We get 1,274.01. So the balance after 3 years is $1,274.01. Write a compound interest function to model each situation, then find the balance after the given number of years. $15,000 invested at a rate of 4.8%, compounded monthly, and then we want to know how much it's worth after 2 years. So step 1, we're going to write the compound interest function for the situation. The formula is A equals P times in parentheses 1 plus R divided by N, close parentheses, raised to the power of N times T. So we're going to substitute $15,000 for the principal. That's the money we invested originally. 0.048 for the R, the rate. That's the rate of interest. And then 12 for N because it's compounded monthly, which means 12 times per year. So we get 15,000 times in parentheses 1 plus, and then it's 0.048 for the rate divided by 12 for how many times it's compounded, and then we're also raised to the power of 12 times t. When we simplify what's in the parentheses, we end up with 1.004. So now we have 15,000 times in parentheses 1.004 raised to the power of 12t. So we're finding the balance after 2 years. We're going to substitute 2 in for t. And then we have to simplify. We're going to multiply 12 times 2 is 24, and then we get 1.004 raised to the power of 24. And then we use a calculator, and then we multiply that by the 15,000, and we get $16,508.22. So the balance after 2 years is $16,508.22. Write a compound interest function to model the situation, then find the balance after the given number of years. $1,200 invested at a rate of 3.5%, compounded quarterly, and they want to know how much it's worth after 4 years. This one's for you to try, and then you can check back for your answer. Step 1 is to write the compound interest function for the situation. So the formula is A equals P times in parentheses 1 plus R divided by N, close parentheses, raised to the power of NT. So we're going to substitute 1,200 for P, that's the money invested, and then 0.035 for R, that's the rate percent as a decimal, and then 4 for N because it's compounded quarterly or 4 times a year. So we get 1,200 times in parentheses 1 plus 0.035 divided by 4, close parentheses, raised to the power of 4 times t. Simplify what's inside the parentheses, and we get 1.00875. So our equation now is 1,200 times in parentheses 1.00875, close parentheses, raised to the power of 4 times t. We're finding the balance after 4 years, so we're going to plug in 4 for t, and then multiply together. 4 times 4 is 16. So we have 1,200 times in parentheses 1.00875 raised to the power of 16, and then we multiply that by 1,200, and we get 1,379.49. So the balance after 4 years is $1,379.49. Write a compound interest function to model the situation, then find the balance after the given number of years. $4,000 invested at a rate of 3% compounded monthly, and they want to know how much it's worth after 8 years. This one's for you to try on your own, and then you can check back for your answer. Step 1, we're going to write the compound interest function for the situation. So the formula is A equals P times in parentheses 1 plus R divided by N, close parentheses, raised to the power of N times T. So we're going to substitute 4,000 for P, that's the money we invested, the principal, and then 0.03 for R, that's our rate of investment, that's the percent as a decimal, and 12 for N because it's compounded monthly, so 12 times a year. So we get 4,000 times in parentheses 1 plus 0.03 divided by 12, close parentheses, raised to the power of 12 times T. We simplify what's inside the parentheses and we get 4,000 times 1.0025, close parentheses, raised to the power of 12t. And we want to find the balance after 8 years. So we're going to substitute in 8 for t. And we get 4,000 times in parentheses 1.0025, close parentheses, raised to the power of 96. And we use a calculator rounding to the nearest hundred. So we get 5,083.47. So the balance after 4 years is $5,083.47. Exponential decay occurs when a quantity decreases by the same rate r in each time period t. Just like exponential growth, the value of the quantity at any given time can be calculated by using the rate and the original amount. So exponential decay is y equals a times in parentheses 1 minus r, close parentheses, raised to the value of t, where a is greater than 0 or positive. Y represents the final amount, a represents the original amount, r represents the rate of decay as a decimal, so you have to convert it by moving it 2 places to the left, and t represents the time. Notice an important difference between exponential growth functions and exponential decay functions. For exponential growth, the value inside the parentheses will be greater than 1 because r is added to 1. For exponential decay, the value inside the parentheses will be less than 1 because r is subtracted from 1. The population of a town is decreasing at a rate of 3% per year. In 2000, there were 1,700 people. Write an exponential decay function to model the situation. Then find the population in 2012. So step 1, we're going to write the exponential decay function for the situation. The formula is y equals a times in parentheses 1 minus r, close parentheses, raised to the value of the power of t. We're going to substitute in 1,700 for a, that's the original amount of people, and 0.03 for r, the rate, that's the percent, the 3% as a decimal. So we get 1,700 times in parentheses 1 minus 0.03, close parentheses, raised to the value of t. And when we simplify, we get 1,700 times in parentheses 0.97, raised to the value of t. And we want to find the population in 2012, which would be 12 years later, so we substitute 12 in for t, and we get 1,700 times in parentheses 0.97 raised to the power of 12. We use a calculator. We're going to round to the nearest whole number because this is people, and obviously there's not going to be part of people. So we get 1,180. So the population in 2012 will be approximately 1,180 people. The fish population in a local stream is decreasing at a rate of 3% per year. The original population was 48,000. Write an exponential decay function to model this situation, then find the population after 7 years. This one's for you to try on your own, and then you can check back for your answer. Step 1 will be to write the exponential decay function for the situation. The formula is y equals a times in parentheses 1 minus r, close parentheses, raised to the value of t, the power of t. We're going to substitute 48,000 for a, that's the original population of the fish, and 0.03 for r, that's the rate of decrease. And so we get 48,000 times in parentheses 1 minus 0.03, close parentheses, raised to the value of t. So when we simplify, we get 48,000 times in parentheses 0.97 raised to the value of t. And we're going to find the population after 7 years, so we're going to substitute 7 in for t, and we get 48,000 times 0.97 raised to the power of 7. And we use our calculator, and we get 38,783. So the population after 7 years will be approximately 38,783, should be fish. A common application of exponential decay is half-life. The half-life of a substance is the time it takes for one half of the substance to decay into another substance. Half-life is A equals P times in parentheses 0.5 or 1/2 raised to the value of T. A represents the final amount, P represents the original amount, T represents the number of half-lives in a given time period. Astatine 218 has a half-life of 2 seconds. Find the amount left from a 500-gram sample of astatine 218 after 10 seconds. Step 1, find T, the number of half-lives in the given time period. So in 10 seconds, we're going to divide that by 2 seconds, which will be the half-life. There are 5 half-lives. So we're dividing the time period by the half-life, and the value of T is 5. That's how many half-lives there are. The formula is A equals P times 0.5 raised to the power of T. We're going to substitute 500 for P, that's the original amount we started with, 500 grams, and 5 for T, that's the amount of half-lives in the time period. So we get 500 times 0.5 raised to the power of raised to the power of 5, and we're going to use a calculator, and we get 15.625. So there are 15.625 grams of astatine 218 remaining after 10 seconds. Astatine 218 has a half-life of 2 seconds. Find the amount left from a 500-gram sample of astatine 218 after 1 minute. So we're going to find T, the number of half-lives in the given period of time. So remember that 1 minute is 60 seconds, and 60 seconds divided by 2 seconds would be 30 half-lives. So T is 30. The formula is A equals P times 0.5 raised to the power of T. So we're going to plug in 500 for P, that's the original amount, we had 500 grams, and 30 for T, that's the number of half-lives in a minute. So we get 500 times 0.5 raised to the power of 30. And we calculate that out, 0.00000047. So there are 0.00000047 grams of astatine 218 remaining after 60 seconds. Cesium-137 has a half-life of 30 years. Find the amount of cesium-137 left from a 100 milligram sample after 180 years. This one's for you to try on your own, and then you can check back for your answer. So we have to find T, the number of half-lives in the given period of time. So 180 years divided by 30 years is 6. There will be 6 half-lives. The formula is A equals P times 0.5 raised to the power of T. So we're going to substitute 100 for P. 100 milligrams is what we started with, the original amount, and 6 for T. That's the amount of half-lives. So 100 times 0.5 raised to the power of 6, we get 1.5625. So there will be 1.5625 milligrams of cesium-137 remaining after 180 years. Bismuth-210 has a half-life of 5 days. Find the amount of bismuth-210 left after a 100-gram sample after 5 weeks. Hint, you need to change 5 weeks to days so that the time measurement is the same. This one's for you to try on your own, and then you can check back for your answer. Find T, the number of half-lives in the given time period. So the number of days in 5 weeks is 35 days, and we're going to divide 35 days by 5 days, and we get 7 half-lives. So the formula is A equals P times in parentheses 0.5 raised to the power of T. So we're going to substitute 100 for P, that's the original amount we started with, 100 grams, and 7 for T, that's the amount of half-lives. So we get 100 times 0.5 raised to the power of 7. Plug it into our calculator, and we get 0.78125. There are 0.78125 grams of bismuth-210 remaining after 5 weeks.